Now let us find out the shear reinforcement. So as per clause B 5.1.1 of IS 456, for beams of varying depth, tau v can be calculated by using this formula. Here there are two signs, plus and minus. So it is also given in the clause that if the bending moment decreases with the decrease in depth, or it increases with the increase in depth, then we have to use the negative sign. See, in our case also, if the depth increases, the bending moment also increases. So we will use negative sign. So here we will put all the values. Vu, the value of Vu is in kilonewtons, so we will multiply it with 1000 to convert it into newtons. Mu is in kilonewton meter, so we will multiply it with 10 to the power 6 to convert it into Newton mm. Beta is this angle. We know this angle is 67.426 degrees. Therefore, the value of beta will come out to be 90 minus 67.426 degrees. So after putting all the values, and again here also the value of B will be equal to the BW, that is the width of the web, and the width of the web is equal to the thickness of the counterfort. So the thickness of counterfort is 600 mm. After putting all the values, we will get tau v equal to 0.46 mm. So this is the amount of shear stress which will come in the counterfort, and this value is lesser than tau c max, which is 2.8 MPa for M20. Therefore it is okay. Now we already calculated the value of PT for AST to be provided for bending moment. So the value of PT was coming out to be 0.16%. Now from table number 19 of IS 456, for PT equal to 0.16% and M20 concrete, we can find out the value of tau C, which will come out to be 0.28 MPa. See, now the value of tau C is smaller than the value of tau V. See, whenever the value of tau C is lesser than the value of tau V, we have to provide shear reinforcement, because tau C is the amount of shear force which will be shear stress which will be resisted by the concrete, but the total stress which is coming is 0.46, so it is much higher than tau C. So therefore, see, since tau C will only be able to resist 0.28%, therefore the remaining part will have to be resisted by the shear reinforcement. So now we will find out the unbalanced shear force, which will be equal to tau v minus tau c into BD. After putting all the values, we will get the value of the shear force, which will come out to be 397.44 kilonewtons. Now we will assume that, see, the horizontal ties, see, now see one thing here. This stem is connected with this counterfort. When the lateral earth pressure acts on the stem, this stem tends to move away from the counterfort, and hence proper connection between the stem and the counterfort has to be provided, so that the joint between the stem and the counterfort does not fail. Similarly, in this case also, where there is a joint between the heel slab and the counterfort, when the net effective pressure acts in the downward direction, the heel slab tends to move or deflect like this. And if there is not any proper connection between the heel slab and the counterfort, the joint will fail. So what we do, in order to provide a proper connection between the stem and the counterfort, we provide horizontal ties. So these horizontal ties are in the form of stirrups, and in order to provide proper connection between the counterfort and the heel slab, we provide vertical ties, and these vertical ties are also in the form of stirrups. So first of all, we will now find out the horizontal ties. So let's come here. See here, in this calculation, it is not the calculation of the horizontal ties or the vertical ties. And these are the stirrups which has to be provided in the counterfort in order to resist the shear reinforcement. So now we are assuming that we are providing two-legged 10-dia stirrups. So ASV, that is the area of cross section of two-legged 10-dia stirrups, can be calculated by this formula, which will come out to be 157.08 mm square. So therefore spacing can be calculated by this formula, which will come out to be 525 mm. But we have to check for the maximum spacing. See, this will be maximum. That what is the maximum spacing that can be provided in the stirrups. So as per IS 456, the maximum spacing is the minimum of these two values, that is 300 mm or 0.75 D. So after calculating 0.75 D, it will come out to be 2760 mm. So the minimum of these two values is 300 mm. Therefore, the maximum spacing is 300 mm, but the spacing is coming out to be 525 mm. And therefore, we cannot give a spacing greater than the maximum spacing. Therefore, we will provide two-legged 10-dia stirrups at the rate 300 center to center. Now we will design the horizontal ties, that is the connection between the stem and the counterfort. See, if you look at this diagram, the only force which tries to move the stem away from the counterfort is the lateral active earth pressure. So now we will have to calculate that how much lateral active earth pressure this counterfort has to resist, so that the horizontal ties need to resist so that the stem so that the joint between the stem and the counterfort does not fail. So see, if you remember the soil pressure distribution diagram, it was something like this. So it was a triangular variation, and the maximum value of the earth pressure was at the bottommost part, and it was 49.93. So so it was 49.93. So now the pressure that has to be resisted per meter run will be, if I multiply 49.93 with the width. See, 49.93 is in kilonewton per meter width. So if I have to find out the earth pressure for per meter width, I will have to multiply it with the width of the T beam, and the width of the T beam, as we already studied, is 4.6. So we will multiply it with 4.6. So we will get the value of the pressure to be resisted as 229.67 kilonewton per meter. Therefore, TU, that is ultimate pressure, will be, just multiply the value with the factor of safety, that is 1.5. So TU will come out to be 344.52 kilonewton per meter. Therefore, the value of AST will come out to be 954.21 mm square. Now again, we will assume that what kind of stirrups do we have to provide in case of the horizontal ties. So we are again assuming that we are providing two-legged 10-dia stirrups. Therefore, the spacing can be calculated by this formula: area of one bar, or area of cross-sectional of the stirrup into 1000, this divided by AST. So area of cross-section of a two-leg 10-dia stirrup will be 2 into pi by 4 into 10 square into 1000, this divided by total area. So the spacing will come out to be this 164, and we can take it as approximately equal to 160 mm, which is also lesser than the maximum spacing, which was 300 mm. Therefore, it is okay. See, now what we do, this spacing that we have calculated for the horizontal ties, we have calculated this spacing by considering the maximum value of the pressure. But if I go in the vertical direction, vertically above, the value of P goes on decreasing. So it is not necessary to provide the horizontal ties at this spacing. The spacing, as we move above, the value of P decreases. Therefore, the value of spacing needs to be increased as we move above. So what we do, we divide this counterfort into three parts. So the bottommost part is h by 3. Okay, h by 3. Again, the next part is also h by 3 height, and the topmost part is also of height h by 3. So now we will find out that see, the horizontal ties that we have just found out, the spacing was coming out to be 160 mm. So we have to use this spacing for this zone, but in this zone the value of pressure has decreased. So now the increased spacing needs to be find out. So what we will do is, we will consider this triangle, and see, if you see this region, in this region the maximum pressure is this. So we will find out the value of this pressure, and the value of this pressure can be found out by using similar triangles. So I have shown you, see, this height is h by 3, so this height will be 2 by 3h. So by using similar triangle, that is the perpendicular of the larger triangle divided by the base of the larger triangle will be equal to perpendicular of the smaller triangle, this divided by the base of the smaller triangle. So the value of pressure at this level will come out to be 2 by 3 times P. So here just the value of P will change, therefore T will change, and hence TU will change, and hence AST will change, and for the AST we can find out the spacing, which will come out to be 240 mm. So in the second zone, that is in this zone, now we have to provide the horizontal ties at a spacing of 240 mm. Now similarly, we will now find out the spacing of the horizontal ties for this topmost zone, that is for a height of h by 3. See, if this height is h by 3, the if this height is h by 3, this height will be 2h by 3. So now we have to see, if you see this region, the value of the maximum pressure is here. So we will now again use similar triangles. One is this triangle and the second triangle is this triangle. By using the similar triangle, we will find out the value of P as 1 by 3 P. So again the value of T will change, and hence TU will change, and hence AST will change, and hence the spacing will come out to be 300 mm. If you will go through this procedure again, the value of spacing will come out to be 300 mm. So therefore, for a zone of h by 3 from the bottom, we have to provide horizontal ties as at a spacing of 160 mm. For for the second zone of height h by 3, we have to provide horizontal ties at a spacing of 240 mm, and for the topmost zone we have to provide horizontal ties at a spacing of 300 mm. So this was a calculation for the horizontal ties. Now we will find out the vertical ties, which will tie the counterfort with the heel slab. So how we calculate the amount of the vertical ties, we will now see. So the vertical ties needs to be provided between the counterfort and the heel slab. See, first of all, we need to see that what kind of force is acting on the heel slab, which is trying to pull this heel out of the counterfort. So on the heel there is only for one force, that is your net effective pressure. So this net effective pressure, which we already found out in the design of the heel slab, will try to move the heel slab away from the counterfort. So now we will see that how do we calculate the vertical ties. See, so during the design of the heel slab, we found out this pressure distribution diagram. This value was 38.02 and the value at the end of the heel slab was 83.97 kilonewton per meter width. So what we do, we take this as the first half, we divide the heel slab into two halves. So for the first half, we first calculate the value of the spacing, and then for the second half, we calculate the value of the spacing. See, if you see the first part, the value, that is the maximum value of the net effective pressure, is 83.97. So we will take the maximum value, 83.97. See, this value is in kilonewton per meter width. So we will multiply it with 4.6, that is width, to get the value in kilonewton per meter. Now TU can be calculated by this formula, 1.5 into T. Then AST can be calculated by this formula. Now again we will assume that suppose we are providing two-legged 10-dia stirrups. So the spacing can be again calculated by the same formula, which will come out to be 97.8 mm. Therefore we will approximately take it equal to 95 mm. Therefore, we will provide two-legged 10-dia stirrups at the rate 95 center to center. So this is the reinforcement which we have to provide for the first half. So now we will see the second half. So now for the second part, we will take the value as 38.02. See, we can take this value, but in this part we have already taken the maximum value, and this value is constantly decreasing. So if you have taken the maximum value in the first half, you can take the minimum value in the second half. If you want to take the maximum value for the second half, we can find out this value by using similar triangles again, and we can use this value for the calculation of the spacing of the vertical ties. But as we had already used the maximum value in the first half, so we can use 38.02 in the second half. So in the second half, I will be going to use the value as 38.02. So this multiplied by 4.6 will give you total T, that is the pressure to be resisted by the vertical ties. Therefore TU can be calculated by this formula, 1.5 into T. AST will come out to be 727.36 mm square. Therefore the spacing can be calculated as 210 mm. So therefore for the second half we will provide two-legged 10 dia at the rate 210 mm center to center. So this was the complete design of the counterfort retaining wall. I hope you all understood from this video. So the whole design of the counterfort retaining wall was divided into several parts, each part showing the design of various components of the counterfort retaining wall.